The notions of space and time are fundamental to our understanding of the universe. We use them to describe the positions and motions of objects, the progression of events, and the very fabric of reality itself. But what if space and time aren't real in the way we commonly perceive them? What if they are emergent properties or illusions created by deeper underlying principles? This question challenges the very foundations of physics and our understanding of reality. Let's explore this profound and intriguing idea. The traditional view of space and time. In classical physics, space and time are considered the stage on which the events of the universe unfold. Newtonian mechanics view space as an absolute, unchanging three-dimensional framework and time as a separate, constant flow. This view dominated scientific thought until the early 20th century. Einstein's revolution. Albert Einstein's theories of relativity revolutionized our understanding of space and time. Special relativity merged space and time into a single four-dimensional continuum known as spacetime, where the separation between space and time is relative to the observer's state of motion. General relativity further showed that spacetime is dynamic and curved by mass and energy, leading to the concept of gravity as the warping of spacetime. Quantum mechanics and the nature of reality. Quantum mechanics, which describes the behavior of particles at the smallest scales, introduces a probabilistic and non-deterministic nature to reality. Unlike the smooth, continuous fabric of spacetime in general relativity, quantum mechanics reveals a world where particles can exist in multiple states simultaneously and where observation affects the outcome. The incompatibility of quantum mechanics and general relativity. Despite their success, quantum mechanics and general relativity are fundamentally incompatible. General relativity describes a smooth, continuous spacetime, while quantum mechanics deals with discrete, probabilistic events. This incompatibility has driven physicists to search for a unifying theory that reconciles these two pillars of modern physics. String theory and the holographic principle. One of the leading candidates for a theory of everything is string theory. It posits that the fundamental constituents of reality are not point particles, but tiny vibrating strings. These strings exist in a higher dimensional space, often requiring 10 or more dimensions. Some versions of string theory suggest that our perception of space and time might be an emergent phenomenon from more fundamental entities. The holographic principle, inspired by string theory, proposes that all the information contained in a volume of space can be represented as a hologram, a description encoded on a lower dimensional boundary. This principle hints that the three-dimensional reality we perceive might emerge from information encoded on a two-dimensional surface. Loop quantum gravity. Another approach to unifying quantum mechanics and general relativity is loop quantum gravity. This theory suggests that spacetime itself is quantized, composed of tiny, discrete loops of gravitational fields. If loop quantum gravity is correct, space and time as we understand them are not continuous but have a granular structure at the smallest scales. Emergent space and time. The idea that space and time might be emergent properties is gaining traction among physicists. Emergence refers to complex phenomena arising from the interactions of simpler elements. Just as temperature emerges from the collective motion of atoms, space and time might emerge from the interactions of more fundamental entities. The possibility that space and time aren't real as we perceive them opens up a frontier of exploration that challenges our understanding of reality itself. As we continue to probe the depths of the cosmos and the intricacies of the quantum world, we may one day uncover the true nature of space and time, transforming our perception of the universe and our place within it.